Okay, so continuing a little bit with arithmetic series, we're going to look now at the sum to n terms of an arithmetic series. Okay, so just a definition of what a sum actually is. A series is a sum where the terms of the sum form a sequence. An arithmetic series is formed by adding together the terms of an arithmetic sequence, obviously. Okay, so we're going to look at how Gauss did this, or Gauss approached this when he was just 10 years old. Okay, so German mathematician Carl Friedrich Gauss was asked by his teacher to find the sum of the first 100 whole numbers, i.e. the answer to 1 plus 2 plus 3 plus 4, all the way up to 100. Okay, so rather than just adding them all together, he tried to look for a shortcut. Okay, so what he looked at is he looked at the sum as it is, 1 plus 2 plus 3 all the way up to 100, okay, but then he reversed that sum and considered 100 plus 99 plus 98 all the way down to 1. And by looking at this way, okay, he could see that if he added those two series together, okay, those two sequences together, and he took basically the first term in each series and then the second term in each series, each time he added them together, he would get 101. And technically, that would be twice the series. So 2s, 2 times the series, was all these 101s added together. And obviously, because there was 100 terms in each series, okay, he had 100 101s. Okay, so 2 times by the series, the sum of the series, okay, was 100 times by 101, in which case one sum of the series was 100 times by 101 divided by 2, which is 5,050. Okay, so he used this to add up all the terms of the first 100 whole numbers. Okay, and likewise, you can do this to add up the terms of any arithmetic series. So, yeah, I guess this poses the question, what were you lot doing when you were 10 years old? Anyway, the first 100 whole numbers form an arithmetic sequence, okay, and that's why this will work, where A is 1, the first term is 1, and D, the difference between all the terms, is also 1. If we use the same idea that Gauss used for any arithmetic series, we can find a formula for the sum of n terms of an arithmetic series. Okay, so I'm going to show you the proof of this. You don't need to know the proof of this, because what's going to happen at the end is you're going to get a formula, and that formula is in fact in your formula sheet. Okay, but it's quite a nice wee proof. Basically goes by what we were doing, or what Gauss did. I can't take claim for his work. In that previous example, okay, but the idea is that the sum of any series, okay, is going to equal, in terms of the longest way of doing it, it's going to equal the first term plus the difference plus the first term plus 2 of the differences, and so on and so forth, up until the first term plus the total amount of terms minus 1 times by the difference. Okay, and in the same way that Gauss did, we can reverse that. And we can, it would look like this, okay, in which case double the sum of the series, okay, would equal those two added together, okay, which you can just hopefully see is 2a plus n minus 1 times by d, okay, in each case, and obviously we have n amount of them, okay, so to add them all together, we have n times by that expression there, 2a plus n minus 1 times by d as well, in which case the sum of an arithmetic series is equal to a half of all of that. Half of n times by 2a plus n minus 1 times by d. Okay, so this is the formula for the sum of an arithmetic series, where we have the following terms. Okay, so you've got 3 different values in here, or 4 technically. Okay, but a is the first term of the series, d is the common difference, and n is the number of terms. Okay, so just what we were doing before with arithmetic series, we can now find the sum of an arithmetic series. So as I say, this formula is given in your formula sheet. The one that we did previously is not, okay, in terms of finding an individual term, but this formula is in your formula sheet, so you don't have to memorize it, and you don't have to know this proof, okay, but it's just quite a nice one, okay. So in terms of examples, find the sum of the first 20 terms of the arithmetic series that starts 3 plus 7 plus 11 plus 15, okay. So because there's only 20, you could just add them all together, but obviously we're trying to deal with a situation where we have much longer series, okay, and we obviously want the shortcut using the formula, okay. So we need to know those 3 things. If we're going to find the sum, we need to know the first term, which we do here. We need to know the difference between the different terms, which we do here. And we need to know the number of terms that we're adding together, which we do. So this is just a case of just shoving everything in the formula, okay. So taking that formula from your formula sheet, and then basically, adding, multiplying, do all the stuff we normally do, 820, okay, for your answer there. Okay, nice and straightforward. But the second example here is slightly different. The reason this is slightly different is because we don't know the number of terms in the series. Okay, so we have to find that out first of all. Okay, so find the sum of this series, but we could work it out. We could kind of just add in all the different terms in between, but that's obviously a bit more of a faff than we'd want. So there is another way of doing it. And if you think back to the formulas that we did initially for our arithmetic series, we can find out how many terms there are by using that, okay? As long as we know that last term, and that's important here because obviously the last term will tell us basically how many terms there are in that series, okay? So we want to use the minus 109 in this formula and then solve it to find n, okay? So we know the first term is 36. We know the difference, we can see the difference between them, okay? It's 5. So if we plug everything into that series, we'll find out, into that formula, sorry, we'll find out what n is by solving that formula, okay? So n will just equal 30. So there are 30 terms there, in which case now we can use it to find the sum of the series by using the formula in our formula sheet, okay? Popping everything in there, we get minus 1095. Okay, right, there is a different way of doing this, but the problem with the other way of doing this is there's a much easier formula, but the formula that I'd use here is only useful in situations like this, and this situation isn't going to come up a massive amount of times, okay? However, if you think back to the way that Gauss did this, okay, we can use a different version of the formula where L is the last term, okay? And this is basically what Gauss was doing. He was adding the first and the last term, he was adding the second term and the second last term, and then multiplying it by how many terms he had, and then dividing it by 2. It's the same kind of idea here. As long as we know those two terms, as long as we know the first and the last, we can actually use this very simple version of the formula. But as I say, you'd have to memorize this formula. It's not on your formula sheet, and it's it's not going to be useful in the majority of situations, okay? But you do get the same answer, so it's up to you. If you want to remember this formula, okay, it's up to you, but it's not going to be used that often, okay? Right, so a slightly different example. How many terms of the arithmetic series 5 plus 8 plus 11 plus whatever the hell are required to make a total of 16,274? Okay, so if you're completely stuck in an exam, you could just keep adding up those series, those terms. Okay, you can see that they go up in 3s, so you can work out all the other ones and just keep adding up until you get to 16,274. But that's quite a big number, so we probably don't want to do that. Okay, so basically what we want to do first of all is use our formula, but we're just going to use it obviously to find the actual sum, the actual n value, sorry, in this series. Okay, so we know the sum of them all. Okay, we just don't know what n is. We know the first term, we know the difference between them, so we're just going to use this formula in reverse to find out what n is. Okay. So working it through, basically what's going to happen, you can see you've got two n's in the formula. If we've got two n's in the formula, it means we're going to end up with a quadratic like so. Right, you can try factorizing that if you want. There's no common factor past this point, but it might be easier in a situation like this to just use the quadratic formula, because then you're finding factors of 3 times 32,548, which again, might be quite complicated. So if you just use the quadratic formula, you'll find out you have these two answers, but obviously you can't have two answers for this, okay? There's not two answers, there's only one possible answer. And the point is the fact that one's positive, one's negative, and since n must be greater than 0, in this case, n is going to equal 103, okay? So as I say, you could have just taken that and you could work out the next 100 terms, and you would see that they would add up to 16,274, but you probably don't want to be doing that in an exam, okay? To be honest, I'm not actually sure you get the marks for that. But so therefore, 103 terms are needed to make the total of 16,274. Lovely. Right. So this last one is a kind of a combination of a bit of everything. So it just depends what you know. So we know the fifth term of an arithmetic series. We know it's 14. And we know the sum of the first 3 terms is minus 3. Okay. We're going to start by calculating the first term, A, and the common difference, D. So we're basically going to set up two formulas here, okay, because of what we know. We know that U5 equals 14, and we know that the sum of 3 terms, of the first 3 terms, is minus 3. Okay, so I'm going to have to use a formula in terms of U5. So the one that I know is UN equals A plus N minus 1 times by D. Okay, and I'm just going to put in as much as I can. Okay, and you can see here that we'll just get A plus 4D equal to 14. Okay, so you'll probably be able to see where this is going by now. Okay, we can't do anything more with that, but we can work on the fact that we know the sum of the first 3 terms is minus 3. Okay, and we can plug what we know into this one. Okay, again, we know what n is. Okay, we know that n is 3 because it's the first 3 terms. We don't know the exact first term. We don't know the difference, but we can get a formula in terms, or we can get an equation in terms of A and D. And when we have 2 equations in terms of 2 variables, then we can solve them simultaneously. Okay, so 3a plus 3d equals minus 3a plus 4d equals 14. And if you solve them simultaneously, just take as much time as you need to do something like that. But the point is, we'll work out that d is 5 and a is minus 6. Okay, so that's the first question answered, and now we can use that to find the next part. But this is slightly different. So given that the nth term of the series is greater than 282, find the least possible value of n. So we're still going to use our initial, or the term in the sequence formula, because we're trying to find the value of n for when we have a term in the sequence that is 282. But we want it to be greater than that, so we're going to change this to an inequality, and we're going to say, basically, we want a plus n minus 1 times by d to be greater than 282, and we use our values for d and a from the previous question. Okay, and we're just going to work it out to find out what n is. Okay, so plugging all that into the equation, we get something like this. Working it all through, we get 5n is greater than 293, in which case n has to be greater than 58.6, in which case the least possible value of n must be 59. Okay, so a few different types of examples in terms of arithmetic series to get you going there. It's a bit more interesting, hopefully, when it gets to the sums, but obviously there's a few more equations to think about and a few different ways of which we can use them.